Medical imaging, it's absolutely central to healthcare today. Letting doctors see inside the body, spot issues, plan treatments.
Totally fundamental. But actually understanding those images, segmenting them, outlining specific bits like organs or maybe tumors, that's a huge challenge.
A massive computational challenge, right?
Yeah.
And precision is key.
Absolutely. You need that pinpoint accuracy for computer-aided diagnosis, for planning surgery. And these images, they can be enormous, so you need methods that are efficient too.
Which brings us to AI. We've seen waves of different models tackling the CNNs, then transformers, each with its own strengths, but also hitting walls.
Limitations.
So today we're doing a deep dive. We've got a pile of notes and studies here on a newer model called Med-URWKV.
Right, based on the RWKV architecture.
Our goal, to really unpack its core ideas, the innovations, what the research actually found, and why you should, maybe pay attention to it.
Sounds good. Let's start with the background. What problems was this model trying to solve? For a long time, the go-to was convolutional neural networks, CNNs, especially the UNet.
UNet, yeah, a real classic for segmentation. What made CNNs like UNet the standard for so long?
Well, they're really good at picking up local details, fine textures, sharp boundaries. CNNs work by looking at small patches, finding patterns there. For segmentation, that's vital.
Okay, so great for the close-up view, but what was the downside?
The main limitation is what's called a restricted receptive field. Basically, each part of the network only sees a small piece of the image. It struggles to grasp the bigger picture.
Like seeing the trees but missing the forest.
Exactly. Understanding how distant parts of the image relate global context or long-range dependencies, that's tough for standard CNN.
Right. It might see a lesion perfectly, but struggle to relate its position to, say, a major organ far away in the scan without lots of complex layers.
Precisely. So to tackle that global context issue, transformers came onto the scene, adapted from language processing success, using self-attention.
Transformers. The idea there was they could connect any point in the image to any other, right? No matter how far apart.
That was the promise. Self-attention lets the model weigh information from everywhere in the image when processing one specific spot. Those long-range connections CNNs missed.
Okay, seems like the solution then. Swap CNNs for transformers.
Not quite that simple. Especially for medical images, transformers have this major drawback: quadratic computational complexity. Meaning, if the image size doubles, the processing power and memory needed can go up by 4 times, maybe even more.
Ouch. That sounds like it would explode with big 3D scans or high-res pathology slides.
It does. That scaling issue is a huge barrier for actual clinical deployment. Hospitals might not have the super high-end GPUs needed to run these efficiently. We also saw mentions of Mamba-based models.
Yeah, what about those?
They offer linear computational complexity, which is much better for efficiency. But the notes suggested sometimes that came at the expense of performance accuracy compared to the best transformers.
Okay, so CNNs, good locally, bad globally. Transformers, good globally, too expensive. Mamba, maybe efficient, but potentially less accurate. Seems like a tricky trade-off.
And that's exactly where the core idea behind Med-URWKV comes in, the Receptance Weighted Key Value model, or RWKV.
RWKV. Okay, how does that fit into this picture?
RWKV is, well, relatively new but gaining traction. It tries to blend the strengths of recurrent networks good at sequences with the parallel training ability of transformers. The sources really highlight 2 things for us.
What's those?
1, it achieves linear computational complexity. So it tackles the transformer cost issue head-on.
Okay, that's big. And 2?
2, it still has a strong capability in capturing long-range dependencies. It avoids the CNN's limited view problem.
Wait, so linear cost and long-range context, that sounds like the holy grail here, addressing both main weaknesses.
That's the claim.
Right.
Plus, it has a parallelizable training architecture, which helps speed up development. The sources even call RWKV a strong contender to potentially replace transformers as a foundational model. Pretty bold stuff.
Okay, high potential. RWKV is the base tech.
Yeah.
How do we get from that to Med-URWKV for medical images?
Well, first there's the adaptation for general computer vision, which is called Vision-RWKV, or VRWKV.
And how did VRWKV do just on regular images?
The notes say it performed really well, sometimes even better than standard vision transformers on benchmarks like ImageNet or 80/20K segmentation, so the vision adaptation itself is solid.
Okay, so VRWKV works well generally, has linear cost, good context. Now, the jump to Med-URWKV, what's the specific, academic innovation here? What makes it stand out in the research?
This is where it gets interesting. The paper emphasizes that Med-URWKV is the first pure RWKV segmentation model in the medical field that can directly reuse a large-scale pre-trained VRWKV encoder.
Okay, lots to unpack there. Pure and reuse pre-trained. Let's take pure first. Why is that significant?
So researchers wanted a pure RWKV architecture, all the key components based on RWKV. Why? To fully exploit the strengths of RWKV.
As opposed to
Previous attempts mentioned in the sources, which were often hybrid CNN RWKV architectures. Maybe an RWKV encoder, but then a standard CNN decoder.
mixing and matching.
Right. And the argument in this paper is that those hybrids fail to fully exploit the advantages of RWKV. You don't see its full potential unless the whole pipeline is RWKV-based. It's an architectural statement, really.
Got it. Fully committing to the RWKV design. Now, what about the reuse pre-trained part? That sounds important, practically.
Hugely important. Their second big goal was building a model that could efficiently leverage these rich, pre-trained VRWKV models developed for general vision. You know, models trained on massive datasets like ImageNet.
Like giving the model a broad visual education before specializing in medicine.
Exactly like that. Using a pre-trained VRWKV means the model already understands basic shapes, textures, patterns. Applying this improves deployment efficiency, less medical data, less training time needed, and you can potentially upgrade easily when better general VRWKV models come out.
And previous medical RWKV models didn't do this.
Apparently not, according to the sources. They were often trained from scratch on just the medical data, missing out on all that foundational knowledge from large-scale pre-training.
So the core academic contribution is twofold. Showing a pure RWKV architecture can work well for medical segmentation, and crucially demonstrating the power of reusing general pre-trained VRWKV models, which hadn't really been done before in this specific context.
That sums it up perfectly. It's about both the architectural purity and the smart reuse of existing knowledge.
Okay, let's get into the structure then.
Yeah.
How do they actually build this pure RWKV model using the UNet shape?
Right, so it keeps the overall UNet framework. That encoder-decoder shape with the skip connections linking them, that structure is proven for segmentation.
But the blocks inside are different. They're RWKV blocks.
Exactly. The core components are VRWKV-based. It starts with the pre-trained VRWKV encoder, takes the input image, extracts features at different levels, and critically, it is pre-trained. The source mentions using VRWKV Tiny trained on ImageNet, then fine-tuned on 8020K. Only the encoder part, though.
So all that general vision knowledge comes in right at the start.
Yes, that's foundational. Then you have an RWKV bottleneck block connecting the encoder and decoder, and then the VRWKV decoder. This part is also VRWKV-based, which is key to the pure architecture idea.
Unlike the hybrid models that use CNN decoders.
Correct. The VRWKV decoder takes features from the bottleneck and, via those skip connections from the encoder, and gradually builds the segmentation map back up. Finally, there's a simple segmentation head, just a lightweight layer to get the final pixel output.
You mentioned earlier the VRWKV block itself has things like spatial mix and channel mix. Can you give us a sense of how those work to achieve the linear cost and long-range context without getting too deep in the weeds?
Sure. So like transformers, the image gets broken into patches, turned into tokens. The VRWKV block processes these. The spatial mix block is where the attention happens, but differently. Instead of comparing everything to everything else like standard attention, which causes that quadratic cost, RWKV uses specific mechanisms. The notes mention a Q-shift mechanism and a bi-WKV mechanism. These basically let the model process tokens sequentially, which keeps the cost linear, but still allows it to effectively gather information and build dependencies from previous tokens. It captures that long-range context efficiently.
So those specific mechanisms, Q-shift by WKV, are the clever engineering bits that allow RWKV to get both efficiency and context.
That's the core idea. It's a different way to achieve a similar goal as attention, but much more efficiently. Then there's the channel mix block, which is more like a standard feed-forward network, processing features within each token across its channels.
Interesting how specific design choices enable those combined benefits.
Okay.
So that's the architecture. UNet shape, pure VRWKV blocks inside, leveraging pre-training. How did they test it? What did the experiments show?
They really put it through its paces, tested it on 7 public medical image segmentation datasets.
7? Wow. What kinds of images?
A real mix: skin cancer, pathology slides, dental x-rays, breast ultrasound, polyps, even wisdom tooth germs in kids. So, different body parts, different imaging methods, pretty comprehensive testing.
And the training process, anything notable there?
Yeah, besides using that pre-trained VRWKV tiny encoder, they had this interesting strategy. For the first 5 epochs, they froze the encoder parameters, kept them fixed.
Froze the pre-trained part initially. Why?
The idea was rapid alignment. It lets the new decoder and bottleneck parts quickly learn how to work with the really good features coming from the frozen pre-trained encoder. Then they unfroze everything and fine-tuned the whole network together. Helps it train faster and more smoothly.
Makes sense. Let the new parts catch up first. Okay, the big question. How did it perform? The results.
The sources, looking at Table I, say Med-URWKV achieved comparable or even superior segmentation performance compared to many established methods across these datasets.
Better than UNet. Better than the transformer types.
It was very competitive, yes. On BUSI, breast ultrasound, for example, it outperformed UNet, SwinUNet, and even some hybrid RWKV models from other studies based on DSC and IOU scores. On Kvasir polyps, Med-URWKV got a 90.93 DSC score, beating SwinUNet's 89.59 and TransUNet's 89.21.
So performance is definitely up there, even beating some well-known models on certain tasks. What about the efficiency angle? Did the linear complexity translate to a smaller model?
Absolutely. That was a key finding. Med-URWKV has around 14.33 million parameters. Compare that to TransUNet with over 92 million, or even a standard UNet around 25 million.
Wow, that's a dramatic difference. Much smaller model. Fewer parameters means less memory needed, potentially faster predictions.
Yeah.
Easier to deploy, right?
Exactly. It really backs up the practical efficiency claims of the RWKV architecture. But maybe the most crucial piece of evidence supporting their main innovation claim comes from the ablation study on pre-training.
Right, this is where they tested the impact of using that pre-trained encoder versus not using it.
Precisely. They compared the full Med-URWKV using the pre-trained encoder against the exact same architecture, but trained entirely from scratch on the BUSI dataset. The results in Table 2 were stark.
What did they find?
The study clearly demonstrated that reusing the pre-trained encoder leads to superior performance and also quicker and more stable convergence. The performance gap was huge. After 100 epochs, the pre-trained model hit 77.34 DSC. The from-scratch model only managed 49.19 DSC.
Whoa, that's not even close. So the pre-training wasn't just a small boost, it was absolutely essential to get those high scores.
Fundamentally essential. It strongly validates their hypothesis that leveraging that large-scale general pre-training is the way to go for getting top performance efficiently with this architecture and medical segmentation. Much better than starting fresh.
Okay, so we've done the deep dive, we've seen the prior landscape, the CNN transformer trade-offs, the RWKV promise, Med-URWKV's pure architecture, and pre-training reuse innovations, the UNet structure with VRWKV blocks, and the strong results on performance, efficiency, and especially the critical role of pre-training shown in the ablation study. Let's tie it all together. What's the bottom line here for you listening?
Well, I think it shows this isn't just, a minor tweak. It points to a really promising direction for AI in demanding fields like medicine. The big takeaway is combining the efficiency of newer architectures like RWKV with the power of large-scale pre-training, all within a consistent, pure design.
And that has real-world implications, doesn't it? A smaller, more efficient model like Med-URWKV is just practically easier to get into clinics. It might run on hardware that's already there. And reusing pre-trained models means less time and potentially less specialized data needed to adapt it to a new medical task.
Exactly. It's a recipe for creating tools that are both cutting-edge, effective, and actually deployable.
Did the researchers mention next steps or limitations?
They did in the preprint. They suggested exploring maybe larger pre-trained VRWKV encoders to see if that pushes performance even higher. Also, designing attention or mixing mechanisms building on those Q-shift by WKV ideas, specifically for pure RWKV medical models.
Refining it further, and presumably a more formal publication is coming with more comparisons.
Right. But this initial work makes a compelling argument for RWKV and pre-training in this space.
Yeah, this whole dive into Med-URWKV really illustrates a broader trend, I think. Taking these powerful general AI foundations, adapting them cleverly for specific domains like VRWKV for vision, and then using smart strategies like pre-training reuse to build specialized tools that are effective and efficient for complex areas like medicine.
It's about that synergy between fundamental AI progress and domain-specific application. Very exciting potential there.
So here's something to think about. This strategy adapts a core AI concept. Specialize it. Leverage pre-training. Where else could that work? What other complex fields, maybe ones you work in or are just curious about, face challenges that could be tackled with a similar approach, taking the best from general AI and tailoring it smartly?
Definitely a question with broad relevance beyond just medical scans.
Worth considering. Well, that brings us to the end of our deep dive on Med-URWKV. Thanks for joining us to unpack the innovations here.
Yeah, understanding these shifts in architecture and methodology is key to tracking where AI applications are headed.
Keep learning, keep exploring.